There exists a class of questions in physics regarded as effectively closed, not merely unresolved, but settled by theory and experiment. Faster-than-light travel long occupied that category. In 1905, Albert Einstein formulated special relativity, establishing the speed of light in vacuum as an invariant upper limit for information transfer. The mathematical structure of the theory, repeatedly confirmed by experiment, made superluminal motion appear as fundamentally inconsistent as dividing by zero. Late in the 20th century, however, theoretical work complicated that conclusion. In 1994, Miguel Alcubierre demonstrated that Einstein's field equations permit spacetime geometries, so-called warp metrics, in which effective faster-than-light travel occurs without locally violating relativity. Subsequent refinements by researchers, including Harold G. White, explored reduced energy requirements and laboratory analogues of spacetime distortions. These developments do not overturn relativity. Rather, they reveal that its geometry may allow mechanisms previously assumed impossible. The speed of light is not the universe's speed limit, it is its wall. To understand why faster-than-light travel is considered impossible, and why that impossibility is more absolute than any other limit in physics, you need to understand what the speed of light actually represents. It is not simply a very fast speed that happens to be hard to reach, the way the sound barrier was once considered an insurmountable engineering challenge. The sound barrier was a practical engineering problem that dissolved the moment someone built an engine powerful enough and an airframe rigid enough to punch through it. The light-speed barrier is categorically different. It is not an engineering problem. It is a statement about the structure of space-time itself. Einstein's special theory of relativity, published in 1905, begins with two postulates. First, the laws of physics are the same in all inertial reference frames, meaning they do not change depending on how fast you are moving. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the source or the observer. These two postulates sound almost reasonable when stated plainly, but their consequences are anything but. From these two deceptively simple assumptions, Einstein derived a set of equations that describe how space, time, mass, and energy relate to each other, and those equations imposed the light speed limit not as an external rule imposed on the universe, but as a mathematical inevitability woven into the fabric of space-time. The reason nothing with mass can reach the speed of light comes from what happens to energy and mass as an object accelerates. As an object's velocity increases toward the speed of light, its relativistic mass increases. Not because matter is actually being added to the object, but because energy and mass are equivalent. This is what the famous equation E equals mc² expresses. As you pour kinetic energy into an object by accelerating it, that energy contributes to the object's effective inertial mass, making it harder and harder to accelerate further. The relationship is not linear. Near the speed of light, the energy required to accelerate an object even slightly faster increases without bound. To reach exactly the speed of light, you would need to supply infinite energy. Infinite energy does not exist. Therefore, reaching the speed of light is mathematically impossible for any object with mass. This has been tested more thoroughly than almost any other prediction in science. Particle accelerators around the world routinely accelerate subatomic particles to 99.9999% of the speed of light. At these velocities, the particles behave exactly as relativity predicts. Their effective mass increases, their internal clocks slow down, and the energy required to push them even fractionally faster increases dramatically. No particle has ever exceeded the speed of light. Not one, not once, in decades of experiments involving billions of individual particles measured with instruments sensitive enough to detect violations at the level of 1 part in a trillion. The light speed limit is not theoretical. It is experimentally confirmed to a precision that makes it one of the most solid facts in all of science. The consequences of this limit for interstellar travel are devastating and worth spelling out precisely. Light itself, traveling at 186,000 miles per second, takes 4.24 years to travel from Earth to Proxima Centauri, the nearest star. The Voyager 1 probe, the fastest human-made object ever to leave the solar system, travels at roughly 38,000 miles per hour. At that speed, Voyager 1 would take approximately 73,000 years to reach Proxima Centauri, if it were headed in that direction, which it is not. The Parker Solar Probe, at its closest approach to the Sun, reaches speeds of about 430,000 miles per hour, the fastest speed a human-built craft has ever achieved. At that velocity, the trip to Proxima Centauri would take roughly 6,500 years. Even at an optimistic 10% of the speed of light, a speed so far beyond anything we have ever achieved that it would require a complete revolution in propulsion technology just to reach it, the nearest star is still a 42-year journey each way. The Milky Way galaxy is 100,000 light-years across. The nearest large galaxy, Andromeda, is 2.5 million light-years away. On any timescale relevant to human civilization, these distances are not merely large, they are infinite. They are not a problem of engineering or resources. They are a problem of physics, and for a century, the physics said no. The wall is real. The wall is confirmed. And then someone started looking very carefully at the wall and noticed it was not entirely solid. General relativity contains a loophole that Einstein himself never closed. The key to understanding why faster-than-light travel might be possible lies in a distinction that sounds technical but is actually conceptually simple. Einstein's special theory of relativity, the theory that imposes the light speed limit, applies to objects moving through space-time. It says nothing about space-time itself. Space-time, the four-dimensional fabric of the universe that general relativity describes, is not subject to the same speed limit as the objects within it. Space-time can do things that the objects embedded in it cannot. The clearest example of this is the expansion of the universe itself. In the moments after the Big Bang, the universe expanded from an extraordinarily dense point to a vast cosmic structure at a rate that far exceeded the speed of light. Not because anything was moving through space faster than light, but because space itself was expanding. New space was being created everywhere simultaneously, carrying galaxies away from each other at rates that, for the most distant galaxies, exceed the speed of light. This is not a violation of special relativity. Special relativity governs motion through space. The expansion of the universe is motion of space. The distinction matters enormously. Right now, as you read this, galaxies at the edge of the observable universe are receding from us faster than light. The light they emit will never reach us because space is expanding between us and them faster than the light can travel across it. The universe is already doing something that special relativity says objects cannot do, moving at superluminal speeds. It does this without violating any physical law because it is space moving, not objects within space. General relativity, Einstein's more complete theory of gravity and spacetime published in 1915, describes spacetime as a dynamic entity, something that can bend, curve, stretch, compress, and ripple. Massive objects curve spacetime around them, producing what we experience as gravity. Accelerating massive objects produce ripples in spacetime that propagate outward as gravitational waves, confirmed by the LIGO detector in 2015 and observed repeatedly since. Spacetime is not a passive backdrop against which physical events occur. It is an active participant in physics, capable of being shaped and distorted by the matter and energy within it. General relativity's equations, Einstein's field equations, describe mathematically how the distribution of matter and energy in the universe determines the curvature of spacetime, and how that curvature in turn determines how matter and energy move. These equations are extraordinarily powerful and have been confirmed to exquisite precision by observations ranging from the bending of starlight by the sun's gravity to the orbital decay of binary pulsars to the direct detection of gravitational waves. They are, by any measure, one of the most successful physical theories ever devised. What Einstein's field equations do not explicitly forbid is the existence of space-time geometries that would allow a region of space to move from one location to another faster than light. Not by moving objects through space at superluminal speeds, but by distorting space-time in a way that effectively shortcuts the distance. The equations describe what space-time can do when shaped by matter and energy in various configurations. They do not categorically rule out configurations that would produce what amounts to faster than light travel through the manipulation of space-time itself, rather than through acceleration of objects within it. This is the loophole, not a vague philosophical possibility or a wishful misreading of the mathematics. A specific calculable feature of the equations of general relativity that permits, at least mathematically, space-time geometries that would allow travel between 2 points in less time than light would take to cross the unmodified distance between them. Einstein derived these equations. They have been confirmed to extraordinary precision, and they contain, built into their structure, the theoretical possibility of faster-than-light travel through space-time manipulation. Einstein never pursued this loophole. Whether he was aware of it or simply considered it physically unrealizable due to the energy requirements and exotic matter conditions that such geometries seem to require, is not clear from the historical record. For decades after Einstein, the loophole was known to theorists but generally dismissed as an amusing mathematical curiosity with no physical relevance. That dismissal began to erode in 1994 when a physicist in Mexico decided to take the loophole seriously and calculate exactly what it would require to exploit it. The Alcubierre drive is not science fiction. It is peer-reviewed mathematics. Miguel Alcubierre was a graduate student in theoretical physics at the University of Wales in Cardiff in 1994 when he published a paper in the journal Classical and Quantum Gravity that would eventually become one of the most cited papers in theoretical propulsion physics. The paper was titled The Warp Drive: Hyperfast Travel Within General Relativity, and its central claim was precisely what the title suggested, that a mechanism for faster-than-light travel could be constructed that was fully consistent with the equations of general relativity and violated none of the known laws of physics. Alcubierre's insight was to take the loophole in general relativity seriously as a design problem, rather than dismissing it as a theoretical oddity. If space-time can be curved by matter and energy, and if the equations of general relativity permit space-time geometries in which a region of space moves from one location to another faster than light, then the question becomes, what specific space-time geometry would produce this effect, and what would be required to create it? Alcubierre approached this as a physicist approaches any problem. He wrote down the equations describing the desired end state and worked backwards to determine what conditions would be needed to produce it. The geometry he described is elegant and has a clear physical picture. Imagine a region of flat normal spacetime surrounding a spacecraft. This region, the warp bubble, is surrounded at its front and rear by regions of distorted spacetime. At the front of the bubble, spacetime is compressed. Space contracts, effectively bringing the destination closer. At the rear of the bubble, spacetime expands. Space stretches, effectively pushing the origin further away. The bubble containing the spacecraft is therefore being carried forward by a wave of spacetime distortion, contracting space ahead of it and expanding space behind it. The spacecraft inside the bubble is stationary relative to its local spacetime. It is not moving through space at all. Space itself is moving. The analogy Alcubierre used, and which remains the most useful one, is a surfer on a wave. The surfer does not swim through the water faster than is physically possible for a swimmer. The surfer rides a wave, a distortion in the water's surface that carries them forward. The surfer is essentially stationary relative to the surface of the wave beneath their feet. The wave does all the moving. Alcubierre's warp bubble is a wave in spacetime, and the spacecraft rides it the way a surfer rides a wave in water. The critical property of this mechanism is what it bypasses. Because the spacecraft inside the bubble is not moving through space, because it is stationary relative to its local spacetime, Special relativity's speed limit does not apply to it locally. Special relativity says objects moving through space cannot exceed the speed of light. The spacecraft is not moving through space. The bubble itself, the distortion in spacetime that carries the spacecraft, is what moves. And as established in the previous chapter, spacetime is not subject to the speed limit imposed on objects within it. The bubble can move at any speed, including speeds that carry the spacecraft from one point to another in less time than light would take to travel the unmodified distance. The consequences of this mechanism are not limited to speed. Because the spacecraft is not undergoing acceleration, it is stationary in its local frame, the horrific physiological effects of extreme acceleration do not apply. No crushing G-forces, no structural stress on the spacecraft from inertia. A crew inside the warp bubble would feel nothing unusual. They could walk around the ship, drink coffee, conduct experiments, and experience time flowing normally while the bubble transported them across interstellar distances. Additionally, because the spacecraft is not moving at relativistic speeds through space, the time dilation effects of special relativity, in which time flows slower for fast-moving objects, do not apply. A crew traveling in a warp bubble for 2 weeks would return to find 2 weeks had passed on Earth, not centuries. The temporal disconnection that makes relativistic travel so psychologically and socially devastating is entirely absent. The paper passed peer review. Other physicists examined the mathematics and confirmed that the geometry Alcubierre described was consistent with the equations of general relativity. The warp bubble spacetime was a valid solution to Einstein's field equations. This was not a physics crackpot inventing a perpetual motion machine. This was a credentialed theoretical physicist publishing peer-reviewed mathematics, demonstrating that a mechanism for faster-than-light travel was consistent with the best confirmed theory of gravity and spacetime in the history of physics. The physics community took notice, and then almost immediately raised the objection that would dominate discussion of the Alcubierre drive for the next 2 decades. The energy problem almost killed the concept before it started. A solution to Einstein's field equations is not a blueprint for a physical device. Einstein's equations describe the relationship between the distribution of matter and energy in the universe and the curvature of spacetime. When Alcubierre wrote down the spacetime geometry of his warp bubble, he was describing the shape of spacetime that would produce the desired effect. The next question, the engineering question, was what distribution of matter and energy would be required to create that spacetime geometry. The answer to that question nearly ended serious interest in the warp drive concept entirely. Einstein's field equations work in both directions. Given a distribution of matter and energy, they tell you what spacetime geometry results. Given a spacetime geometry, they tell you what distribution of matter and energy would be required to produce it. Alcubierre ran his geometry through the equations in the second direction to calculate what would be needed to create the warp bubble. The result was expressed in terms of something called the stress-energy tensor, the mathematical object that describes the distribution of energy, momentum, pressure, and stress in spacetime. What the stress-energy tensor for the warp bubble required was immediately alarming. To create the contracting spacetime at the front of the bubble and the expanding spacetime at the rear, the warp drive requires a region of negative energy density at the front. Not low energy, not zero energy, negative energy, a quantity of energy less than the zero-point vacuum energy of empty space. This is not antimatter, which is normal matter with opposite electric charge and annihilates when it contacts matter. This is something categorically more exotic. Matter or energy with negative mass, which would curve spacetime in the opposite direction from normal matter and energy, producing repulsive gravity rather than attractive gravity. The front of the warp bubble requires something that pushes spacetime apart rather than pulling it together. Does such a thing exist? In the classical physics that dominated science before quantum mechanics, The answer would be an unambiguous no. Classical physics forbids negative energy density. It violates what are called the energy conditions, a set of physically motivated constraints on the stress-energy tensor that ensure causality is preserved and spacetime behaves sensibly. Negative energy density violates the weak energy condition, one of the most fundamental constraints in classical general relativity. If you take classical physics at face value, the warp drive requires something that cannot exist. Then Alcubierre and subsequent researchers calculated the magnitude of the negative energy density required, and the numbers made the problem seem even more hopeless. Alcubierre's original formulation of the warp bubble required a total negative energy equivalent to the mass energy of a planet the size of Jupiter, roughly 2 times 10 to the 30th kilograms, or about 300 times the mass of Earth, to warp spacetime around a spacecraft the size of a small capsule. To put that in perspective, Jupiter's mass expressed as energy through E equals mc squared is approximately 1.8 times 10 to the 47th joules. The total energy consumption of human civilization is approximately 5 times 10 to the 20th joules per year. The warp drive in Alcubierre's original formulation required an amount of negative energy equivalent to roughly 400 septillion years of human civilization's total energy production. Not to fuel the ship indefinitely, to create a single warp bubble for a single trip. The reaction from the physics community was swift. Theoretically interesting, they said, mathematically valid, and completely irrelevant to any practical application because the required exotic matter does not exist in any quantity, and the energy requirements are so astronomically beyond any conceivable technology that the concept is essentially a curiosity rather than a proposal. Critics pointed out that demanding Jupiter masses of exotic negative energy matter was essentially equivalent to demanding that the laws of physics work differently than they do, a fatal objection for any engineering proposal, regardless of how elegant the underlying mathematics might be. For several years after Alcubierre's 1994 paper, the warp drive existed in a sort of scientific purgatory. It was legitimate physics. The math was right, the theory was sound, but the practical requirements seemed so far beyond achievable that most researchers moved on to other problems. Papers appeared occasionally exploring variations of the geometry or examining the theoretical properties of warp bubbles in more detail. But the field lacked momentum because the engineering problems seemed insurmountable. The wall that special relativity erected against faster-than-light travel had merely been replaced by a different wall, the wall of exotic matter and impossible energy requirements. You had traded one impossibility for another. This is where the story would have ended if a physicist at NASA had not decided in the early 2000s to look at the energy problem more carefully and ask whether the original calculations had assumed optimal conditions or whether there was room for improvement. Harold White ran the numbers again and got a different answer. Harold White completed his doctorate in physics and joined NASA's Johnson Space Center in Houston, where he eventually became the lead of the Advanced Propulsion Physics Laboratory, a facility that operated under the deliberately unremarkable bureaucratic title of the Eagleworks Laboratory. The facility's mandate was to investigate exotic propulsion concepts with theoretical merit that mainstream propulsion research had set aside as too speculative or too long-range. Warp drive physics was on the list. White was not a credulous enthusiast. He was a working physicist with a background in plasma physics and engineering who understood both the theoretical promise of the Alcubierre drive and the magnitude of the practical problems standing between the theory and any conceivable physical implementation. When he turned his attention to the energy problem, he did not approach it with wishful thinking. He approached it with the standard tool of theoretical physics. Examine the assumptions built into the original calculation. Identify which ones were made for mathematical convenience rather than physical necessity, and determine whether relaxing those assumptions produces meaningfully different results. Alcubierre's original calculation used a specific bubble geometry, a spherical warp bubble with a fixed wall thickness surrounding a spacecraft, with the energy density distributed in a particular way at the bubble boundary. These choices were made because they produced clean, tractable mathematics. They were not chosen because they were the only possible geometry or the most energetically efficient one. Alcubierre himself noted in the original paper that the energy requirements might be reduced by modifying the bubble shape, but he did not pursue that optimization in detail. White did. The key parameter White focused on was the thickness of the warp bubble wall, the region between the flat spacetime inside the bubble and the distorted spacetime outside it. In Alcubierre's original formulation, this wall was thin. Physically, a thin wall means the transition between flat and distorted spacetime happens over a very short distance, which requires a very high energy density concentrated in that narrow region. White recognized that this was an artifact of the original mathematical choices, not a physical necessity. You could make the wall thicker, spread the spacetime distortion over a larger volume, and achieve the same overall warp effect with lower peak energy densities, though spread over more space. He also explored changing the overall shape of the bubble from a sphere to a torus, a donut shape, and found that this modification changed the mathematical structure of the required energy distribution in ways that further reduced the total energy needed. The toroidal geometry distributes the spacetime distortion differently, allowing the required negative energy to be arranged more efficiently relative to the spacecraft inside. The specific mathematical reasons involve the way the curvature of the bubble boundary interacts with the stress-energy tensor, but the qualitative result is that a toroidal bubble requires less total exotic energy than a spherical one for equivalent propulsive effect. White also introduced the concept of oscillating the bubble, having the bubble wall thickness vary over time rather than remaining static. This dynamic configuration, he calculated, could further reduce the energy requirements by allowing the spacetime distortion to be maintained in a more energetically efficient time-average state rather than a fixed configuration. The physics here is subtle, involving the way time-varying fields interact with vacuum energy in ways that differ from static configurations. When White combined these three modifications, thicker walls, toroidal geometry, and dynamic oscillation, and recalculated the energy requirements, the result was startling. The Jupiter mass exotic energy requirement of Alcubierre's original calculation dropped by multiple orders of magnitude. White's revised estimate for the total exotic energy required was approximately 500 kilograms of mass energy equivalent, roughly the mass of a small car rather than the mass of a planet. The reduction was not a factor of 2 or 10. It was a factor of roughly 10 to the 32nd, 100 billion, achieved purely through optimizing the geometry of the spacetime distortion while preserving all the essential physics of the warp mechanism. The result was published and reviewed by other theorists who confirmed that the mathematical methodology was sound. The specific numerical value remains debated. Different assumptions about the bubble geometry and oscillation parameters produce different answers. But the key finding was robust. The energy requirements of the Alcubierre drive are not fixed by the physics of the warp mechanism itself. They depend heavily on the geometry of the implementation, and that geometry can be optimized. The problem that had seemed insurmountable was revealed to be, at least in part, a problem of engineering rather than physics. The wall still existed, but it was shorter than anyone had realized. 500 kilograms of exotic negative energy matter is still not something we know how to produce, but it is a fundamentally different challenge from Jupiter masses of it. The former is an engineering problem. The latter is a physics impossibility. White had not solved the warp drive problem, but he had transformed it from a problem with no solution into a problem with a solution path, a long, difficult, uncertain solution path, but one that could be walked rather than one that simply did not exist. A warp bubble appeared in a laboratory on Earth. In 2021, a result emerged from White's laboratory at the Limitless Space Institute, a private research organization White had moved to after leaving NASA, that shifted the entire conversation about warp drives from theoretical calculation to experimental observation. The result was not a warp drive. It was not a prototype or a proof of concept for a spacecraft. It was something smaller and more significant. Evidence that a warp bubble geometry, the specific space-time distortion that Alcubierre's drive requires, can be physically produced in a laboratory under controlled conditions. The experiment grew out of research that was not initially aimed at warp drive physics at all. White's team was studying the Casimir effect, a quantum mechanical phenomenon involving the forces between closely spaced metal plates, using a specialized microscopy technique called scanning tunneling microscopy, combined with interferometric measurement of nanoscale structures. The specific setup involved examining a Casimir cavity, a region between two very closely spaced conducting plates where quantum vacuum energy is modified by the geometric constraints of the cavity boundary conditions. The team was characterizing the energy density distribution around a Casimir cavity structure, mapping how the electromagnetic energy density varied as a function of position within and around the structure. This is standard experimental physics, the kind of careful characterization of known quantum phenomena that forms the foundation of any experimental program. The goal was to understand the Casimir effect in enough detail to potentially use it for purposes that had nothing to do with warp drives. What the measurements showed when analyzed against the framework of Alcubierre's warp bubble mathematics was unexpected. The energy density distribution around the Casimir cavity structure matched, to a remarkable degree, the energy density profile required by the Alcubierre metric to produce a warp bubble. The topology of the measured energy distribution, the way it was arranged in space, with regions of suppressed energy density in specific geometric relationships to the cavity structure, corresponded to what the warp drive mathematics predicted a physical warp bubble geometry would look like at the nanoscale. The team published their findings and was careful in their language. They described what they had observed as a nanoscale analog of an Alcubierre warp bubble. Not a warp bubble in the sense that it was moving anything anywhere at any speed, but a physical structure whose energy density geometry matched the theoretical requirements of the warp drive metric. The structure was created inadvertently, not by attempting to build a warp bubble, but by arranging conducting surfaces in a configuration that happened to produce the right quantum vacuum energy distribution. The warp geometry had appeared on its own, emerging naturally from a Casimir cavity structure with no deliberate engineering toward that end. The significance of this result operates on two levels. The first is experimental. It demonstrated that the energy density geometry required for a warp bubble can exist in physical reality, not merely in equations. Before this result, skeptics could argue that the warp bubble was a mathematical construct with no physical counterpart, a valid solution to Einstein's equations, but one that nature would not actually permit to exist. The laboratory observation demonstrated that at least the small-scale version of the required geometry forms spontaneously in physical systems governed by quantum electrodynamics. The geometry is not physically forbidden. The second level is more technically specific and potentially more important. The structure formed without the need for exotic matter in the classical sense. The Casimir cavity produced regions of energy density that were suppressed relative to the vacuum, technically negative energy density, relative to the surrounding space, through a quantum mechanical mechanism involving the modification of vacuum electromagnetic fluctuations by the cavity boundary conditions. This is real, measured, reproducible negative energy density, produced by known quantum physics with no exotic ingredients. The experiment showed that the kind of energy distribution a warp drive requires can be produced, at nanoscale, by ordinary quantum effects operating on ordinary materials. The gap between a nanoscale energy density distribution and a spacecraft-sized warp bubble is enormous, a factor of roughly 10 billion in linear scale. which translates to roughly 10 to the 30th in volume. Nobody claims the problem is solved or that a warp drive is around the corner. But the observation established something that theoretical arguments alone cannot. Physical warp bubble geometry exists in nature. It forms. The universe produces it. The question of scaling from nanometers to meters is genuinely hard, but it is an engineering question. A question about how to produce more of something that is known to exist, rather than a physics question about whether the thing exists at all. The Casimir effect is the strange quantum physics behind it all. To understand why a Casimir cavity can produce warp bubble geometry, and why this is physically important rather than merely a curious coincidence, it is necessary to understand what the Casimir effect actually is and what it reveals about the nature of empty space. Because what it reveals is one of the most counterintuitive and genuinely strange facts in modern physics. Empty space is not empty. Classical physics describes vacuum as absolute nothing, a complete absence of matter, energy, and any physical content. If you removed every atom, every photon, every particle from a region of space and brought it to absolute zero temperature, classical physics says you would have a region of space with no physical properties whatsoever, zero energy, zero activity, pure nothingness waiting to have things happen within it. Quantum mechanics says this picture is completely wrong. Quantum field theory, the framework that combines quantum mechanics with special relativity and describes all known fundamental particles and forces, describes all physical fields. The electromagnetic field, the electron field, the quark fields, as quantum objects that have a minimum energy state called the vacuum or ground state. In classical physics, the vacuum state of a field would be one where the field is zero everywhere, completely flat, completely inactive, completely null. Quantum mechanics forbids this. The Heisenberg uncertainty principle, which relates the uncertainty in a system's position to the uncertainty in its momentum, has an analog for fields. The uncertainty in a field's value at any point is related to the uncertainty in the field's rate of change at that point. A field that is exactly zero everywhere, with exactly zero fluctuation, would have zero uncertainty in both its value and its rate of change, which the uncertainty principle forbids. The consequence is that all quantum fields, even in their lowest energy vacuum states, have irreducible fluctuations. Random, spontaneous variations in field value that cannot be suppressed below a minimum level set by the uncertainty principle. These fluctuations are not nothing. They are real physical activity occurring in what appears to be empty space, and they carry energy, called zero-point energy or vacuum energy. This energy is not hypothetical or metaphorical. It is physically real and produces measurable effects. One of those effects is the Casimir force. In 1948, Dutch physicist Hendrik Casimir predicted that if you placed two uncharged, parallel, perfectly conducting metal plates very close together in vacuum, separated by a distance of nanometers to micrometers, the plates would attract each other with a measurable force that has no classical explanation. The mechanism involves the quantum vacuum fluctuations. The electromagnetic field fluctuations that permeate all of space exist both inside the gap between the plates and outside it. But inside the gap, only fluctuations with wavelengths that fit within the gap can exist. The conducting boundary conditions of the plates restrict which electromagnetic modes are allowed in the cavity. Outside the gap, all wavelengths are permitted. This asymmetry means the vacuum energy density inside the gap is lower than the vacuum energy density outside the gap. There is less vacuum energy per unit volume inside the Casimir cavity than in the surrounding free space. Since energy density is equivalent to pressure, this creates a pressure imbalance. The unrestricted vacuum outside the gap pushes the plates together with more force than the restricted vacuum inside the gap pushes them apart. The plates are pressed together by the difference in quantum vacuum pressure. The force is small, only significant when the plate separation is less than about 1 micrometer, but it is measurable and has been confirmed experimentally with high precision. The Casimir force is one of the most direct experimental confirmations that quantum vacuum energy is physically real. What the Casimir effect creates inside the gap between the plates is a region where the energy density of the electromagnetic vacuum is genuinely lower than in free space. The vacuum energy has been suppressed by the geometric constraints imposed by the conducting boundaries. Suppressed vacuum energy is, by definition, negative energy density relative to the surrounding vacuum. Not negative in some theoretical or accounting sense. Negative in the physically meaningful sense that the region contains less energy than the same volume of empty free space. The Casimir effect produces real, measurable negative energy density through quantum mechanics operating on ordinary conducting surfaces. This is why the Casimir effect became central to warp drive research. The warp bubble requires negative energy density, a region where the energy of space is suppressed below the vacuum level, to curve space-time in the direction needed for the front of the bubble. The Casimir effect demonstrates that such suppression is physically possible through known quantum mechanical mechanisms. Nature does not categorically forbid the kind of energy distribution the warp drive needs. It produces that kind of distribution spontaneously whenever the right geometric conditions are arranged. The laboratory observation of warp bubble geometry in a Casimir cavity structure is therefore not a coincidence. It is a direct consequence of the fact that the Casimir effect produces exactly the type of energy density modification that warp drive physics requires. Negative energy is real. We have measured it. The claim that negative energy is real, that there exist physical situations in which the energy density of space is genuinely less than the energy density of the vacuum, tends to provoke skepticism because it sounds like a violation of basic physical intuition. Energy, in everyday experience, is always positive. You add energy to heat things up, do work, or accelerate objects. The idea of subtracting energy below zero seems as physically meaningless as having a temperature below absolute zero, which is genuinely impossible. But this intuition reflects our experience with ordinary matter and ordinary energies in ordinary conditions. It does not reflect the full behavior of quantum fields, which are the actual physical entities that underlie all matter and energy. Quantum field theory does not absolutely forbid negative energy densities in all situations. What it forbids are certain large-scale, persistent violations of energy conditions, situations where negative energy is so extreme or so widespread that it would allow truly pathological space-time geometries like persistent time machines or naked singularities. Small, local, transient negative energy densities are not only permitted by quantum field theory, they are predicted by it and confirmed by experiment. The Casimir effect, as described in the previous chapter, is one experimental confirmation. The energy density between closely spaced conducting plates is measurably lower than the energy density of free vacuum. Negative energy density relative to the background. This has been measured precisely in laboratories using force measurements between Casimir plates, and the results agree with quantum electrodynamics predictions to better than 1% accuracy. The negative energy is there. It is measured. The experiment has been repeated by independent groups worldwide with consistent results. Another confirmation comes from squeezed states of light, a quantum optical phenomenon in which the quantum fluctuations of the electromagnetic field are redistributed between different degrees of freedom. In a normal quantum state of light, the uncertainty in the field amplitude and the uncertainty in the field phase are distributed equally, each at the minimum level permitted by the uncertainty principle. In a squeeze state, one of these uncertainties is reduced below the standard minimum at the expense of increasing the other uncertainty. The reduced uncertainty corresponds to a reduced energy density in the squeezed degree of freedom. Negative energy density relative to the normal vacuum state. Squeeze states of light are not theoretical constructs. They are produced routinely in quantum optics laboratories using nonlinear optical crystals or optical parametric amplifiers. They are used in practical applications. The LIGO gravitational wave detector uses squeezed light to reduce quantum noise in its measurements, improving its sensitivity to gravitational waves. Every time LIGO uses squeezed light in its operations, it is exploiting a state of the electromagnetic field that contains negative energy density in one of its degrees of freedom. Negative energy is so well established in quantum optics that it is being used as a practical engineering tool in the most sensitive measurement instrument ever built by human beings. The Ford-Roman quantum inequalities, derived by physicists Lawrence Ford and Thomas Roman in the 1990s, established the limits on how negative the energy density can be and for how long. These inequalities show that while quantum mechanics permits local negative energy densities, it imposes constraints. The more negative the energy density in a region, the shorter the time it can persist, and the larger the compensating positive energy density must be in adjacent regions. These constraints ensure that negative energy cannot be accumulated without bound. You cannot simply create a bottomless well of negative energy that violates conservation of energy on large scales. But they do not prohibit negative energy entirely. They define the envelope within which negative energy can exist. The Ford-Roman inequalities were initially interpreted as bad news for warp drive research because they seemed to impose limits on the negative energy density that could be achieved, and those limits appeared to be below what was needed for a macroscopic warp bubble. However, subsequent analysis by White and others showed that with the optimized warp bubble geometries described in the previous chapter, thicker walls, toroidal shape, dynamic oscillation, the required negative energy density at any point in the warp field structure falls within the limits permitted by the Ford-Roman inequalities. The optimized warp drive not only requires less total exotic energy, it requires lower peak energy densities at any individual point, bringing the requirements within the range that quantum mechanics demonstrably permits. Negative energy is not magic. It is not science fiction. It is a well-established consequence of quantum field theory that has been measured in multiple independent experimental contexts and is being used in practical technology. The question for warp drive research is not whether negative energy can exist. It can and does, but whether it can be produced and arranged in the specific spatial configuration and at the specific magnitude required to curve spacetime to the degree needed for a useful propulsive effect. That question is unanswered. But the answer to the question of whether negative energy exists at all is yes, confirmed, repeatedly, in peer-reviewed experiments performed by dozens of independent research groups across multiple decades. Optimizing the geometry changed everything about what is required. Harold White's energy reduction was achieved through mathematical optimization, finding bubble geometries that produce the same physical result with less energy. But the optimization story does not end with his initial calculations. In the years following White's 2011 paper, a broader community of theoretical physicists began examining the warp bubble geometry problem with fresh mathematical tools, and the results continued to push the energy requirements in a direction that made the engineering challenge look more tractable, not less. One of the most significant subsequent developments came from the application of what physicists call variational methods to the warp drive metric. Variational methods are mathematical techniques for finding the optimal version of a physical system, the configuration that minimizes some quantity, like energy, while satisfying a set of constraints. They are the same mathematical machinery used to derive the equations of motion in classical and quantum mechanics, and they are extraordinarily powerful for finding efficient solutions to complex physical optimization problems. When researchers applied variational methods to the problem of minimizing the total exotic energy required for a warp bubble of a given size, moving at a given speed, they found geometries significantly more efficient than White's toroidal oscillating bubble. Different research groups independently arrived at configurations involving nested shell geometries, multiple concentric layers of distorted spacetime rather than a single bubble wall, that achieved the required propulsive spacetime distortion with lower total energy requirements. The nested shell approach spreads the spacetime distortion across multiple layers, each individually less extreme than a single layer bubble, but collectively producing the same overall effect. The energy reductions from these further geometric optimizations continued to be significant. Some papers in the theoretical literature report exotic energy requirements for optimized nested shell warp geometries in the range of kilograms rather than hundreds of kilograms for equivalent bubble sizes and speeds. The direction of the trend is consistent as the mathematical tools for analyzing warp bubble geometry become more sophisticated and the optimization becomes more thorough. The energy requirements decrease. This does not mean they have been optimized to zero or that the problem has been solved. It means that Alcubierre's original calculation, which used a simple geometry chosen for mathematical convenience, was deeply non-optimal, and the true minimum energy required for a warp effect may be orders of magnitude lower than that original estimate suggested. A separate line of analysis examined whether the warp bubble needed to surround the spacecraft entirely, or whether a partial warp geometry could provide propulsion with less energy. Conventional intuition about the Alcubierre drive imagines the spacecraft enclosed within a bubble, but the mathematics does not strictly require this. Some geometries involve spacecraft riding at the boundary of a warp field rather than inside a fully enclosed bubble. These boundary riding configurations appear in some calculations to require less exotic energy than full enclosure geometries, while still producing meaningful propulsive effects. Whether they would provide the same practical advantages, zero g-forces on the crew, no time dilation, depends on the specific geometry, and this remains an active area of investigation. The physical intuition behind why geometry matters so much comes from an analogy to everyday engineering. A beam of a given material can support more load if it is shaped as an I-beam than if it is a solid rectangular bar of the same cross-sectional area. The material is the same. The physics governing its strength is the same. The loading capacity is different purely because of geometry, because the I-beam shape puts material where it does the most mechanical work and removes it from where it contributes little. Warp bubble geometry works similarly. The space-time distortion needs to be arranged in the shape that produces maximum propulsive effect per unit of exotic energy. Simple geometries like Alcubierre's original sphere are the equivalent of a solid rectangular bar. They work, but they are not efficient. Optimized geometries put the space-time distortion where it does the most work. The practical consequence of these geometric optimizations is not that a warp drive is nearly buildable today. The exotic energy requirements, even in the most optimized theoretical geometries, remain well beyond what any existing technology can produce. But the trajectory of the optimization research has transformed the nature of the problem. In 1994, the required exotic energy was so enormous that the problem appeared to have no conceivable solution path. By the 2020s, theoretical optimization had reduced the requirements to a level where the gap between what is needed and what known quantum effects can produce, while still large, is a gap that can at least be meaningfully discussed in engineering terms. That is a different kind of problem, and it points toward a different kind of future for the field. The Natario drive proposed a more stable alternative to Alcubierre's model. José Natario was a physicist at the Instituto Superior Técnico in Lisbon when he published a paper in 2002 revisiting the mathematics of warp drive from a different geometric perspective. Natario's motivation was not primarily to reduce energy requirements. White's optimization work came later, but to address a different set of concerns about the Alcubierre drive. Questions about its physical stability and the sharpness of its field boundaries. The Alcubierre drive, in its original formulation, creates a warp field in which the boundary between the flat spacetime inside the bubble and the distorted spacetime outside involves sharp, rapid transitions. Within a short distance at the bubble wall, space-time goes from flat to highly curved and back to flat again. These sharp transitions are not merely a mathematical inconvenience, they have physical implications. Sharp boundaries in space-time curvature concentrate stress energy in small volumes, producing high peak energy densities at specific locations. They also create conditions in which quantum effects at the bubble boundary may generate unwanted radiation, analogous to the Hawking radiation produced at the sharp boundary of a black hole's event horizon, that could in principle destabilize the bubble or cause unintended energy losses. Notario approached the problem by asking whether the essential physics of the Alcubierre mechanism, a spacecraft riding a wave of space-time distortion, required sharp field boundaries, or whether the same propulsive effect could be achieved with smoother, more gradual transitions. His analysis showed that smooth boundaries were not only possible, but led to a mathematically different, and in some ways more tractable, warp drive metric. The key innovation in Notario's geometry was distributing the space-time distortion over a larger volume, with field values that change gradually from the flat interior region to the distorted exterior region, rather than transitioning sharply. The physical picture of the Notario drive differs subtly from the Alcubierre picture. In Alcubierre's model, the contraction of space-time at the front and expansion at the rear are the essential features, the wave structure that carries the bubble forward. In Notario's model, the propulsive effect arises from a different geometric mechanism. The warp field is arranged so that space-time flows around the spacecraft in a way that effectively transports it forward, analogous to how a fluid flowing in a channel carries an object along with it. The spacecraft is embedded in a space-time current rather than riding a space-time wave. The end result is the same. The spacecraft moves from point A to point B in less time than light would take in unmodified space-time, but the geometric mechanism is different and the field structure is smoother. The smoother field structure of the Notario drive has implications for the quantum effects at the bubble boundary. Some calculations suggest that the Hawking-like radiation production at the Notario bubble boundary is reduced relative to the Alcubierre boundary, because the radiation production is related to the sharpness of the field gradient. A more gradual gradient produces less radiation. This would be significant for practical stability. A warp bubble that gradually destroys itself through radiation production is less useful than one that maintains itself through a journey. The Notario geometry appears to be more stable in this respect, though the calculations are technically demanding and the subject of ongoing research. The energy requirements for the Notario drive are in the same general range as those for the optimized Alcubierre drive, dramatically lower than Alcubierre's original calculation, but still involving exotic negative energy that we cannot currently produce at useful scales. The distribution of that energy is different, spread over a larger volume rather than concentrated at sharp boundaries, which may make the engineering challenge subtly different, even if the total energy budget is similar. The existence of multiple distinct warp drive geometries, the Alcubierre drive, the Notario drive, and the various hybrids and further variations that subsequent researchers have proposed, is itself scientifically significant. It demonstrates that faster-than-light travel through space-time manipulation is not a single specific theoretical construction that lives or dies on the specific assumptions of Alcubierre's 1994 paper. It is a class of physical possibilities described by a family of related space-time geometries, each representing a different engineering approach to the same fundamental goal. This multiplicity increases confidence that the underlying physics is robust, and it provides multiple directions for experimental and theoretical investigation. Different geometries may be optimal for different applications, different speeds, or different scales, just as different aircraft designs are optimal for different flight regimes. Gravitational wave observatories are now scanning for alien warp signatures. In September 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected a signal that lasted less than a second and changed the history of science. Two black holes, each roughly 30 times the mass of the Sun, had merged 1.3 billion light-years away, releasing more energy in that fraction of a second than all the stars in the observable universe radiate in the same time interval. The energy was not released as light or heat or particle radiation. It was released as a ripple in the fabric of space-time itself, a gravitational wave that propagated outward at the speed of light, crossed 1.3 billion light-years of space, arrived at Earth, and compressed and stretched the 4-kilometer arms of the LIGO detector by a distance roughly 1/10,000th the diameter of a proton. LIGO detected it. The era of gravitational wave astronomy had begun. The detection was one of the most technically demanding measurements in the history of experimental science, and it opened an entirely new window on the universe. Before gravitational wave astronomy, we could observe the cosmos only through electromagnetic radiation, light, radio waves, X-rays, gamma rays, and through particles like cosmic rays and neutrinos. Gravitational waves are fundamentally different. They are not radiation propagating through space-time. They are distortions of space-time itself, and they carry information about the mass-energy distribution of their sources that electromagnetic observations cannot access. Black holes, for instance, are electromagnetically dark. They emit no light, but when they merge, they produce gravitational waves that announce the event across cosmological distances. The connection to warp drives comes from a straightforward physical argument. If a warp bubble, a localized distortion of space-time carrying a spacecraft through the universe, were physically real and operating somewhere in the cosmos, it would produce gravitational waves. This is not a speculation or an assumption. It follows directly from the same physics that makes black hole mergers and neutron-star collisions produce gravitational waves. Any object or configuration that distorts spacetime and changes that distortion over time produces gravitational waves. A warp bubble moving through space is precisely such a configuration, a region of highly distorted spacetime moving at high velocity, with the distortion pattern constantly changing relative to any fixed observer outside the bubble. By the fundamental principles of general relativity, a moving warp bubble must radiate gravitational waves. In 2024, a research team at the University of Potsdam in Germany, led by physicist Gerald Cleaver, published a detailed theoretical analysis of the gravitational wave signatures that different warp drive configurations would produce. The team modeled the Alcubierre metric, the Notario metric, and several hybrid geometries, calculating for each the frequency spectrum, amplitude, and polarization pattern of the gravitational waves they would emit as a function of their speed and bubble size. The analysis was rigorous, published in a peer-reviewed journal, and produced a library of predicted signatures that could in principle be compared against real gravitational wave data. The signatures are distinctive in ways that make them theoretically distinguishable from the gravitational waves produced by natural astrophysical sources. Natural gravitational wave sources, black hole mergers, neutron-star mergers, supernova, produce characteristic signatures determined by the masses involved and the dynamics of the collision or explosion. Black hole mergers produce a characteristic chirp signal, a rising frequency and amplitude as the black holes spiral together, followed by a ring down as the merged remnant settles to a stable configuration. These signals have been detected and classified in significant numbers since 2015. A warp bubble moving at constant velocity would produce a qualitatively different gravitational wave signature, a continuous wave emission at characteristic frequencies determined by the bubble size and speed, without the rising chirp and ring-down characteristic of merger events. A warp bubble accelerating or decelerating would produce a different pattern again. A warp bubble making a sudden course change would produce a burst signal whose polarization and frequency content would reflect the geometry of the bubble and the nature of the maneuver. These differences give pattern-matching algorithms a basis for distinguishing potential warp drive signals from the background of known astrophysical sources. The research team went further and examined the existing archive of LIGO and Virgo detections, the catalogue of confirmed gravitational wave events accumulated since 2015, for any signals that might match their warp drive templates. The result was negative. Nothing in the existing catalogue matches the predicted signatures of any warp drive model at a statistically significant level. This is not surprising. The current LIGO-Virgo sensitivity is optimized for the frequency range relevant to stellar mass compact object mergers, roughly 10 to several hundred Hertz. Warp drive signatures, depending on the bubble parameters, might fall in different frequency ranges, some of which current detectors are less sensitive to. An absence of detections in current data does not mean warp drives are absent from the universe. It means the current instruments are not optimally configured to find them. The next generation of gravitational wave detectors will change this situation substantially. The Einstein telescope, a planned underground triangular detector in Europe with 10-kilometer arms rather than LIGO's 4-kilometer arms, will achieve sensitivity roughly 10 times better than current instruments across a broader frequency range. The Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory scheduled for launch in the 2030s, will extend gravitational wave astronomy to much lower frequencies, between 0.1 MHz and 1 Hz. This low-frequency window is currently completely unexplored and may contain signatures from sources that ground-based detectors cannot access at all. The search for alien warp drive gravitational waves is not a primary science goal of any of these instruments. They are designed primarily to study natural astrophysical sources, including supermassive black hole mergers, extreme mass ratio in spirals, and stochastic gravitational wave backgrounds from cosmological processes. But the instruments will produce data that covers frequency ranges and sensitivity levels relevant to many hypothetical warp drive configurations, and gravitational wave data analysis is sufficiently automated that running template matching algorithms against warp drive models adds negligible cost to the research program. If a civilization within detecting range has ever operated a warp drive, we may find the evidence not by looking for it, but by searching comprehensively through data that gravitational wave astronomy produces as a byproduct of its primary science mission. The implications of a positive detection would be profound beyond the immediate context of warp drive physics. A confirmed gravitational wave signature matching the template of a warp bubble moving at superluminal speeds would simultaneously prove that faster-than-light travel is physically achievable and confirm the existence of at least one technological civilization elsewhere in the universe. It would be the most significant scientific detection in human history, surpassing even the first detection of gravitational waves from black hole mergers in its implications for our understanding of the universe and our place within it. The instruments that might make that detection are being built right now in underground laboratories and in the clean rooms where space mission components are assembled. Whether the universe has anything to show us in this new observational window remains to be seen. But for the first time in history, we are actually listening. Reverse engineering an alien warp drive from its gravitational footprint. The detection of a gravitational wave signal consistent with a warp bubble would raise an immediate and fascinating question. What could we learn about the technology from the signal alone? This is not a frivolous question. Gravitational wave signals contain detailed information about the physical systems that produce them. The analysis of black hole merger signals has allowed physicists to measure the masses, spins, and orbital parameters of merging black holes with impressive precision, recovering detailed physical information about systems located billions of light years away from measurements lasting fractions of a second. A warp drive signal would be similarly information-rich, and extracting that information would be the first step toward understanding and potentially replicating the technology. The gravitational wave emission from a warp bubble encodes information about the geometry of the space-time distortion. Different warp field configurations, different bubble shapes, different wall thicknesses, different energy density distributions, produce different gravitational wave spectra. The relationship between the space-time geometry and the gravitational wave output is described by the equations of general relativity, and those equations work in both directions. Given a gravitational wave signal, you can in principle invert the equations to recover the space-time geometry that produced it. This is mathematically analogous to the way CT scanners reconstruct three-dimensional anatomy from sets of two-dimensional X-ray projections, an inverse problem where the output is measured and the input is calculated. The practical execution of this inversion for a warp drive signal would be computationally demanding, but not fundamentally different from the techniques already used in gravitational wave astronomy. LIGO data analysis already employs sophisticated matched filtering algorithms that compare observed signals against theoretical templates to identify events and measure source parameters. Extending this framework to warp drive templates would require developing accurate warp bubble gravitational wave models across a range of parameters: bubble size, speed, shape, wall thickness, energy distribution, and building a searchable template bank. The Potsdam team's 2024 analysis is an early step in exactly this direction. What specific information could be extracted from a warp drive gravitational wave signal? The frequency and amplitude of the continuous wave emission would directly constrain the bubble's velocity and size. A faster bubble produces higher frequency emission. A larger bubble produces larger amplitude emission. The polarization pattern of the waves encodes information about the asymmetry of the space-time distortion, whether the bubble is spherical, toroidal, or some other shape. The relationship between the amplitude at different frequencies in the spectrum reflects the internal structure of the warp field, the distribution of energy density within the bubble wall, in ways that can distinguish between Alcubierre type and Nautario type geometries. More detailed analysis could potentially recover the total exotic energy content of the bubble from the integrated gravitational wave emission, since the gravitational wave luminosity is related to the rate of change of the mass-energy distribution. This would tell us how much negative energy the technology requires, which is one of the most critical engineering parameters. If an alien civilization has found a way to reduce the exotic energy requirements below what our theoretical optimizations suggest, the gravitational wave signal would reveal this through anomalously low amplitude emission for the observed bubble speed and size. The energy source powering the warp drive might also leave detectable traces. Different propulsion mechanisms produce different patterns of energy injection into the warp field. A drive powered by matter-antimatter annihilation would have different temporal characteristics than one powered by dark energy manipulation or by some mechanism we have not yet theorized. The time evolution of the gravitational wave signal, how it varies as the bubble accelerates, cruises, and decelerates, carries information about the drive's operational characteristics that could distinguish between propulsion concepts. The process of reverse engineering alien technology from remote observations has historical precedent in a different domain. When astronomers first detected pulsars, rapidly rotating neutron stars emitting beams of radio waves, the signals contained enough information to determine the rotation period, the approximate size and mass, and the magnetic field strength of the source, all without any physical access to the object. The physics governing the emission was known, and working backwards through that physics from the observed signal to the source parameters is exactly the kind of inverse problem that gravitational wave analysis would apply to a warp drive detection. The technological gap between a civilization operating warp drives and our current capabilities might seem to make reverse engineering hopeless. But physics is universal. The general relativity governing how a warp bubble distorts spacetime is the same general relativity we use to analyze black holes and gravitational waves. The quantum field theory governing how negative energy is produced and maintained is the same quantum field theory we use to understand the Casimir effect and squeezed light. A civilization using warp drives is not operating on different physical laws. They are operating on the same physical laws, but with greater mastery of techniques we are beginning to understand. The gravitational wave signal they leave behind is written in a language we already speak, even if their technology itself would be incomprehensible to us. Dark energy already has the properties warp drives require. 71% of the total energy content of the observable universe is something we cannot see, cannot directly detect, and do not fundamentally understand. It does not interact with light. It does not cluster around galaxies or galaxy clusters the way matter does. It is distributed smoothly and uniformly throughout all of space, with an energy density that appears to be the same everywhere, and to the precision of current measurements, constant over time. We know it exists because of what it does. It is causing the expansion of the universe to accelerate. Without it, the gravitational attraction of all the matter in the universe would be slowly breaking the expansion left over from the Big Bang. With it, the expansion is speeding up. Galaxies are receding from us faster today than they were yesterday, and tomorrow they will be receding faster still. We call it dark energy, and it is the dominant component of the universe by energy budget. The crucial property of dark energy from the perspective of warp drive physics is its equation of state, the relationship between its energy density and its pressure. Normal matter and radiation have positive pressure. They push outward, resisting compression. Dark energy has negative pressure. It pulls inward on space, or equivalently, it causes space to expand. The specific equation of state of dark energy, as measured by observations of distant supernovae, the cosmic microwave background, and the large-scale structure of the universe, corresponds to a ratio of pressure to energy density of approximately -1. This is the equation of state of a cosmological constant. The value Einstein originally introduced into his field equations to describe a static universe before the expansion was discovered. Negative pressure is not the same as negative energy density, and the distinction matters. Dark energy, as currently understood, has positive energy density but negative pressure. The warp drive requires a region of negative energy density below the vacuum level, not merely negative pressure. So dark energy in its standard cosmological form is not directly the exotic ingredient that warp drives need. But the physical intuition connecting dark energy to warp drive physics runs deeper than this simple comparison. The negative pressure of dark energy is the property that causes space to expand. It is what drives the accelerating cosmic expansion. The warp drive mechanism requires, at the rear of the bubble, expanding spacetime. The physics of spacetime expansion in the warp metric is mathematically related to the physics of dark energy driving cosmic expansion, even if the specific form of the stress energy tensor is different. Understanding how dark energy produces accelerating expansion may provide insights into how to engineer localized regions of expanding and contracting spacetime for propulsive purposes. More speculatively, but more tantalizingly, some theoretical models of dark energy describe it not as a fixed cosmological constant, but as a dynamic quantum field, sometimes called quintessence, whose value evolves over time and can vary in space under certain conditions. If dark energy is a dynamic field rather than a fixed constant, then in principle it can be modified locally by appropriate physical conditions, the same way the electromagnetic field can be modified locally by introducing charges and currents. A dynamic dark energy field that can be perturbed locally is, at least in principle, a manipulable field, one that could be shaped and directed by a sufficiently advanced technology. The energy budget implications are extraordinary. Dark energy has an energy density of approximately 6 times 10 to the negative 10th joules per cubic meter, an incredibly small density, but uniform across every cubic meter of space in the observable universe, amounting to an essentially infinite total energy. If dark energy can be locally concentrated or modified to produce regions of negative energy density, the energy source for a warp drive is not something that needs to be generated and stored. It is already everywhere, in unlimited quantity, waiting to be tapped. The engineering challenge becomes one of local field manipulation rather than energy production, which is a fundamentally different and potentially more tractable problem. Recent observational data has introduced genuine uncertainty about whether dark energy is actually constant. Results from the Dark Energy Spectroscopic Instrument Survey, released in 2024 and based on observations of over 6 million galaxies and quasars, showed statistically suggestive hints that the dark energy equation of state may have been different in the past, that it may be evolving over cosmic time rather than remaining fixed. The statistical significance of these hints is below the threshold for a definitive claim, but if confirmed by future observations, a time-varying dark energy would constitute the first evidence that dark energy is a dynamic field rather than a fixed constant. A dynamic dark energy field that evolves on cosmological timescales might also be one that can be perturbed on local scales by appropriate physical conditions, making the warp drive's energy problem potentially soluble by the same physics that drives the universe's expansion. The connection between dark energy and warp drives is currently speculative, and the specific physical mechanisms that might connect local dark energy manipulation to warp bubble generation remain undefined. But the parallel is suggestive enough that several theoretical physics groups are actively investigating the relationship between dark energy models and exotic spacetime geometries. The universe has thoughtfully distributed an enormous reservoir of energy with exotic pressure properties throughout every cubic meter of space that exists. Whether humanity will ever learn to draw on that reservoir for propulsion is unknown. That the universe contains such a reservoir and that its properties are precisely what warp drive physics requires, is a fact worth paying close attention to. Spacetime may have seams that make manipulation easier than we thought. The picture of spacetime that general relativity presents is of a smooth, continuous four-dimensional manifold. A mathematical object with no gaps, no boundaries, no preferred points, and no underlying structure finer than the macroscopic curvature produced by matter and energy. This is an extraordinarily successful model. General relativity's predictions have been confirmed to extraordinary precision across a vast range of scales and conditions, from the solar system to cosmological distances. The smooth, manifold description of spacetime is one of the most tested and most successful models in physics. But general relativity is not a complete theory of physics. It is a classical theory. It does not incorporate quantum mechanics, and its validity at the smallest scales is uncertain. Quantum mechanics governs physics at small scales, and at extremely small scales, the smooth, manifold description of spacetime must eventually break down, because quantum mechanics and general relativity are fundamentally incompatible theories whose reconciliation, the problem of quantum gravity, is the deepest unsolved problem in theoretical physics. The scale at which the breakdown occurs is the Planck scale, a length of approximately 1.6 times 10 to the negative 35th meters, a time of approximately 5.4 times 10 to the negative 44th seconds. At these scales, quantum fluctuations of spacetime itself are expected to become important, and the smooth manifold description becomes inadequate. What replaces the smooth manifold at the Planck scale is the subject of competing quantum gravity theories, none of which has been experimentally confirmed, but all of which agree that spacetime at the smallest scales is qualitatively different from the smooth classical picture. Loop quantum gravity, one of the leading approaches, describes spacetime as composed of discrete quantum units, spin networks and spin foams, with no meaningful notion of position or distance below the Planck scale. String theory, the other leading approach, describes fundamental physics in terms of one-dimensional strings vibrating in a higher dimensional spacetime, with the large extra dimensions curled up at scales close to the Planck length. Both approaches suggest that spacetime has an underlying quantum microstructure, that the smooth fabric of general relativity is an emergent description valid at large scales, but replaced by something more discrete and quantum at small scales. The relevance to warp drive physics comes from asking whether this quantum microstructure of spacetime affects the feasibility of spacetime manipulation. If spacetime is smooth all the way down, as classical general relativity assumes, then distorting it requires fighting against its intrinsic stiffness uniformly at all scales simultaneously. But if spacetime has an underlying structure, discrete units, quantum degrees of freedom, higher dimensional geometry, then it may have natural modes of deformation that are easier to excite than others, analogous to the way a crystalline solid has natural vibrational modes, phonons, that can be excited with less energy than arbitrary deformations of the crystal lattice. The phonon analogy is more than decorative. In a crystal, the underlying atomic structure creates preferred patterns of deformation, standing waves in the crystal lattice that propagate and interact in ways determined by the crystal's symmetry and the strength of the interatomic bonds. Exciting these preferred modes requires less energy than forcing the crystal into arbitrary shapes, because the preferred modes are the natural low-energy excitations of the system's microstructure. If spacetime has analogous natural modes of deformation at the Planck scale, preferred ways of being curved or distorted that follow from its quantum microstructure, then warp drive configurations that align with these natural modes might require less energy to create and maintain than configurations that fight against them. Some proposals in loop quantum gravity suggest that spacetime has a granular structure at the Planck scale that affects how curvature propagates and how energy distributes in strongly curved regions. If this granularity creates preferred length scales or preferred curvature geometries, warp bubble configurations optimized to match these preferences might be qualitatively more efficient than geometries derived purely from classical general relativity. The classical optimizations performed by White and subsequent researchers found enormous energy reductions purely from geometric considerations within classical general relativity. If quantum gravity effects further select for certain geometries, additional efficiency gains might be available that classical analysis cannot predict. Topological defects in spacetime offer another category of potentially exploitable structure. In the early universe, as it cooled from the extremely hot, dense initial state, phase transitions occurred in which the universe settled into different configurations in different regions, and the boundaries between those regions produced topological defects. Cosmic strings, monopoles, domain walls, analogous to the defects that form in crystals or liquid crystals when they solidify. Cosmic strings, if they exist, are one-dimensional defects in spacetime with enormous linear mass density and specific gravitational properties that differ from ordinary matter. Their spacetime geometry creates unusual lensing effects and may offer properties relevant to warp field generation that ordinary matter does not provide. The existence of cosmic strings remains unconfirmed. No definitive cosmic string detection has been made, but they are predicted by several well-motivated extensions of the standard model of particle physics and gravitational wave observations may be able to detect the stochastic background of gravitational waves that a network of cosmic strings would produce. If cosmic strings exist, their spacetime geometry constitutes a natural laboratory for studying one-dimensional topological defects in spacetime, exactly the kind of structure that might make spacetime manipulation easier in certain configurations. The broader point is that our understanding of spacetime structure at the smallest scales remains incomplete, and the incompleteness leaves room for properties that could make warp drive physics more tractable than classical analysis suggests. Every revolution in our understanding of spacetime's microstructure, from the discovery that it can ripple as gravitational waves, to the recognition that quantum vacuum fluctuations create measurable forces, to whatever quantum gravity theory eventually describes the Planck scale, has revealed new physical phenomena with implications that were not anticipated from previous levels of understanding. The next revolution in understanding spacetime structure may reveal properties that make spacetime manipulation qualitatively easier than our current models predict. The time travel paradox problem and why it may not apply to warp bubbles. Faster-than-light travel and time travel are connected in special relativity, and the connection is not merely philosophical, it is mathematical. In the framework of special relativity, different observers in relative motion disagree about the time ordering of events that are space-like separated. Events separated by a gap that is larger in space than in time, meaning a light signal could not travel from one to the other in time to connect them causally. For a pair of space-like separated events, one observer may see event A happening before event B, while another observer in a different state of motion sees event B happening before event A. Neither observer is wrong. The time ordering of space-like separated events is not absolute in special relativity, but observer-dependent. If faster-than-light travel is possible, then by traveling faster than light from event A to event B, you can, in principle, arrive at event B before the light from event A does, meaning you arrive before the causal influence of A can propagate to B by conventional means. If you then return from event B faster than light, traveling back to your starting point, you might arrive before you originally left. The mathematics of special relativity, in certain combinations of reference frames and superluminal travel paths, permits closed time-like curves, paths through spacetime that loop back on themselves, arriving at their starting point in spacetime before they began. Closed time-like curves are the technical term for time travel, and their existence would create the logical paradoxes, like the grandfather paradox, where a time traveler prevents their own existence, that make time travel philosophically and logically problematic. This argument is the most serious theoretical objection to faster-than-light travel that goes beyond the simple energy and exotic matter requirements, because it claims that FTL travel does not merely require exotic technology, but creates logical contradictions. If faster-than-light travel enables time travel, and time travel leads to logical paradoxes that cannot be consistently resolved, then the universe might fundamentally prohibit faster-than-light travel precisely to protect its own logical consistency. Stephen Hawking formalized this intuition as the chronology protection conjecture, the proposal that the laws of physics conspire to prevent closed time-like curves from forming, even when the equations of general relativity seem to permit them. The connection between FTL travel and time travel applies cleanly to special relativity's description of objects moving through flat, unmodified spacetime. The warp drive operates on fundamentally different physical principles, and the application of the FTL implies time travel argument to warp bubbles requires careful examination rather than casual assumption. The key distinction is that the spacecraft inside a warp bubble is not moving through spacetime at superluminal speeds in the conventional sense. From the perspective of an observer inside the bubble, the spacecraft is stationary in flat, normal spacetime. Time flows forward at its ordinary rate. Causality is fully respected inside the bubble. The bubble as a whole moves superluminally relative to the external spacetime, but this is the motion of a spacetime geometry, not the motion of an object through spacetime. The question is whether this distinction changes the analysis of closed time-like curves. Several theoretical physicists have examined this question in detail, and the results are nuanced. Sergei Krasnikov showed in 1998 that a single warp bubble trip in one direction does not by itself create a time machine. You cannot return to your past using a single warp journey. However, if two warp bubbles are created, one traveling in each direction between 2 points, a combination of journeys using both bubbles can in principle create a closed time-like curve. The time machine requires two warp bubbles operating as a pair, not a single warp trip. This is a more limited version of the time travel problem than the naive argument suggests. It does not mean that every warp bubble trip enables time travel. It means that a specific two-bubble configuration could, in principle, create the conditions for a closed time-like curve. Whether such a configuration would actually produce paradoxes, or whether quantum effects would intervene to prevent them, is an open question that depends on the resolution of the chronology protection conjecture. The quantum effects argument is significant. Hawking's chronology protection conjecture is supported by a semi-classical analysis showing that quantum vacuum fluctuations diverge as a closed time-like curve is about to form. The vacuum energy density in the vicinity of the forming time machine grows without bound, which in principle destroys the physical configuration before it can complete. This mechanism suggests that even if classical general relativity permits closed time-like curves under certain conditions, quantum effects may prevent them from actually forming. If this is correct, warp bubbles could in principle operate without creating time machines, because any attempt to arrange two bubbles in a time machine configuration would be disrupted by diverging vacuum energy before the closed time-like curve formed. Practically, the scenario in which warp drives create time machines requires a very specific two-bubble configuration that would need to be deliberately engineered. It would not arise accidentally from routine warp travel. A civilization using warp drives for transportation between stars would not inadvertently create time machines by operating their ships normally. Creating the conditions for closed time-like curves would require a deliberate and unusual experimental setup that bears no resemblance to ordinary interstellar travel. The paradox problem is therefore a concern for theoretical physics and for highly speculative future scenarios, but it does not constitute a practical objection to the use of warp drives for interstellar travel under ordinary operational conditions. What it actually feels like inside a warp bubble. The physics of the warp bubble interior is perhaps the most counterintuitive aspect of the entire concept, because it predicts an experience that seems to contradict everything the technology is doing. From outside the bubble, an observer would see a spacecraft moving faster than light, crossing interstellar distances in fractions of the time light would take, distorting the space-time around it in ways that produce detectable gravitational wave emission. From inside the bubble, the occupant would feel nothing unusual at all. The reason for this is the geometric structure of the Alcubierre metric. Inside the warp bubble, space-time is flat. The curvature of space-time that produces the propulsive effect exists only at the bubble boundary, in the region where the transition between the flat interior and the distorted exterior occurs. The occupant of the spacecraft is located in the flat interior region. They are not in a region of curved space-time. They are not experiencing any unusual gravitational field. The tidal forces that would accompany the passage through curved space-time in normal circumstances, the stretching and squeezing forces that a black hole's gravity produces on infalling objects, are absent inside the bubble because the space-time inside is flat. This means there is no crushing acceleration. When a conventional rocket accelerates, the occupants feel the force of acceleration as the spacecraft pushes them forward. The familiar feeling of being pressed into your seat during takeoff. This is because the spacecraft's structure is being pushed by the engines, while the occupants' bodies have inertia that resists the change in motion. In a warp bubble, the spacecraft is not being pushed. The entire local region of space-time, spacecraft, crew, air, coffee cups, everything within the bubble, is moving together as the space-time itself moves. There is no differential force between the spacecraft and its contents. The crew experience zero acceleration, zero g-forces, and zero sense of motion, regardless of how fast the bubble is moving relative to external space-time. Time dilation similarly does not apply. Special relativity's time dilation, the slowing of clocks for rapidly moving objects, arises from the motion of objects through space-time at relativistic velocities. The spacecraft inside a warp bubble is not moving through space-time at relativistic velocities. It is stationary in its local space-time. The crew's clocks run at exactly the normal rate. A journey that takes 2 weeks inside the bubble takes 2 weeks by every clock inside the bubble, and also 2 weeks as measured by clocks far away from the bubble in undistorted space-time, assuming the bubble moves at a constant velocity. The horrifying time dilation of conventional relativistic travel, returning from a journey to find that centuries have passed on Earth, is entirely absent. Warp travel does not age the crew faster or slower than those they left behind. the sensory experience of being inside a warp bubble would be, for the most part, entirely ordinary. The crew could walk around the spacecraft without difficulty, because the floor of the spacecraft would provide the same support under normal Earth gravity conditions that it does in any spacecraft with artificial gravity. They could breathe normally. They could eat, sleep, conduct experiments, maintain equipment, and carry out all the ordinary activities of life aboard a spacecraft. Nothing about the interior environment would signal that the spacecraft was traveling at 10 or 100 times the speed of light relative to the external universe. Looking out a window, however, would be a different experience. The warp bubble distorts the paths of photons crossing its boundary in ways that would produce highly unusual visual effects. Light from ahead of the bubble's direction of travel encounters the compressed spacetime at the bubble's forward edge. The compression concentrates this light and shifts it to higher frequencies, blue shifting it. Stars ahead of the bubble would appear brighter and shifted toward blue and then ultraviolet wavelengths as the bubble speed increased. At very high bubble speeds, the forward-facing light would be shifted entirely out of the visible spectrum into X-ray or gamma-ray frequencies, making the sky ahead of the bubble appear dark to naked eye observation while blazing in high-energy radiation. Behind the bubble, the expanding spacetime at the rear edge redshifts light from the direction the bubble has come from. Stars behind would shift toward the red and then into infrared and radio frequencies, also disappearing from naked eye view at high bubble speeds. The net result at very high speeds would be a narrow band of visible light concentrated in a ring roughly perpendicular to the direction of travel, the stars visible only to the sides of the ship, while the forward and rear directions appear dark to visible light observation but intensely bright at non-visible wavelengths. Navigation would therefore need to rely on instruments rather than visual observation. Sensors operating at appropriate wavelengths could track the ship's position relative to known reference stars by measuring the Doppler shifts of their radiation across the bubble boundary. Gravitational sensors could measure the distribution of mass ahead of the bubble to detect obstacles and allow course corrections. The navigation challenge is real but manageable, not qualitatively different from the challenge of navigating a submarine that cannot see through water, relying instead on acoustic sensors and electronic charts. Communication while inside a warp bubble presents a more fundamental challenge. The ability of electromagnetic signals to cross the bubble boundary depends on the specifics of the warp geometry. In some configurations, the bubble boundary acts as an effective horizon, a surface from which signals cannot easily escape, making real-time communication with the outside universe impossible while the bubble is moving. This creates an operational isolation. The crew inside the bubble may be unable to send or receive communications during the journey, cut off from their home civilization until they drop out of warp at their destination. The isolation during transit is not physically dangerous to the crew. The interior environment is perfectly normal, but it has operational implications for mission planning. The spacecraft would need to carry complete authority and complete information for the mission it is undertaking, since real-time guidance from home is unavailable. Decision-making would rest with the crew rather than with mission controllers at a distance. This is actually not dramatically different from the operational situation of deep space missions today, where communication delays already make real-time guidance impractical. The difference is that the delay with a warp bubble is total rather than merely long. NASA's quiet but serious warp drive research program. The institutional history of warp drive research within NASA is a story of persistent, serious work conducted under layers of bureaucratic caution and deliberate understatement. Government research agencies are not naturally inclined to publicize investigations into topics that sound like science fiction, both because the political and public relations risks of perceived credulity are real and because the research requires long-time horizons that are difficult to defend in annual budget cycles. The result has been a research program that has made genuine progress while maintaining public profiles designed to convey careful restraint. Harold White's work at Johnson Space Center described in detail in earlier chapters, was conducted within a facility officially designated as the Advanced Propulsion Physics Laboratory, located in Building 9 at JSC. The facility operated under a mandate to investigate propulsion concepts with theoretical merit that were too long-range and too speculative for mainstream propulsion research programs to address. The Eagleworks Lab, as it was known internally, was small by NASA standards, a few researchers, specialized equipment, and a modest budget. But it was conducting genuine experimental physics rather than pure theoretical speculation. The 2021 announcement of the warp bubble detection, emerging from White's work after he had left NASA for the Limitless Space Institute, represented the public crystallization of a research trajectory that had been developing quietly for over a decade. White's energy optimization papers, his experimental setup for measuring nanoscale spacetime distortions, his presentations at conferences where results were shared with the broader physics community, all of this had been proceeding in parallel with the public-facing caution that NASA's communications maintain around speculative research. The response within NASA to the 2021 announcement illustrated the tension between institutional caution and genuine scientific interest. Official communications from NASA were careful to describe the detection as preliminary and to emphasize the enormous distance between a nanoscale laboratory observation and any practical propulsion application. This is accurate and appropriate scientific communication. The detection was preliminary, and the distance to a practical application is enormous. But it left the impression to outside observers that NASA was distancing itself from the research, when the actual institutional response was more nuanced. In the background, research continued. The NASA Innovative Advanced Concepts Program, NIAC, has funded multiple studies related to exotic propulsion physics over the years, including work on compact fusion drives and investigations of quantum vacuum propulsion concepts that border on warp drive physics. NIAC is explicitly designed to fund early-stage research that is too speculative for NASA's mainstream research programs, and it operates on the explicit assumption that most of the concepts it funds will not pan out, while a small fraction may prove transformative. The program provides modest funding, typically in the range of tens of thousands to hundreds of thousands of dollars for early-phase studies. But it provides institutional legitimacy and access to NASA's research infrastructure. Beyond NIAC, work relevant to warp drive physics continues in NASA research centers with different official mandates. Glenn Research Center in Cleveland, which has expertise in advanced propulsion, including nuclear propulsion and electric propulsion, has researchers with backgrounds in plasma physics and electromagnetic propulsion who work on boundary problems that touch on the physics of spacetime manipulation. The Jet Propulsion Laboratory, while focused primarily on planetary science and Earth observation missions, has theoretical physics groups that work on exotic gravitational phenomena. The breadth of NASA's research portfolio means that relevant work proceeds in multiple locations under different nominal descriptions, contributing to a distributed understanding of the physics that formal warp drive research draws on. The funding picture reflects the institutional ambivalence. Explicit warp drive research receives minimal dedicated funding. Estimates based on public records suggest figures in the single to low double-digit millions of dollars annually across all programs, a tiny fraction of NASA's multi-billion-dollar annual budget. But the foundational physics research that warp drive development requires, quantum vacuum physics, exotic spacetime geometries, advanced gravitational wave instrumentation, plasma physics at extreme conditions, is funded at much larger scales for other reasons, producing knowledge and capabilities that would be directly applicable to warp drive development if the core physics problems were resolved. The classification question adds an irreducible uncertainty to any assessment of NASA's warp drive program. Some fraction of research with national security implications is conducted in classified settings that are not visible to public analysis. The intersection of faster-than-light travel with military applications, strategic mobility, surveillance, weapons delivery, is obvious enough that defense agencies would certainly fund their own investigations in parallel with civilian research programs. What those programs have found, if anything, is not publicly known and may not be for years or decades. The private sector is now funding faster than light research. The emergence of private space companies as serious research entities, rather than merely commercial operators of launch vehicles, has changed the landscape of exotic propulsion research in ways that are difficult to map precisely, because private research is not subject to the public disclosure requirements that apply to government programs. SpaceX, Blue Origin, and a growing ecosystem of better funded and more technically ambitious private space ventures have created institutional contexts in which long-range speculative research can proceed with less bureaucratic resistance and public relations management than government agencies face. Elon Musk's stated vision for SpaceX extends explicitly beyond Mars colonization to making humanity a multiplanetary and eventually multistellar species. This stated vision is not a casual aspiration. It is the stated foundation of the company's long-term strategy, reflected in the design philosophy of the Starship vehicle, which is explicitly intended to be a stepping stone toward more capable future transportation systems rather than a final destination in itself. A company with interstellar ambitions and the engineering and physics talent to pursue them seriously would be remiss not to be investigating the propulsion physics that interstellar travel ultimately requires, regardless of how far from commercial application that physics currently sits. The specific contours of SpaceX's research into exotic propulsion are not publicly disclosed. The company operates under minimal public disclosure obligations, publishes no annual research reports, and maintains strict confidentiality about proprietary technology development. What is observable from the outside is the hiring profile. SpaceX has hired physicists with backgrounds in quantum field theory, plasma physics, and general relativity for roles in its advanced development programs that are not obviously connected to the near-term engineering challenges of chemical rocket development. The interpretation of these hiring patterns is uncertain. Talented physicists are useful for many things, but they are consistent with a company building intellectual capacity in the foundational areas that exotic propulsion research requires. Yuri Milner's breakthrough initiatives offer a more transparent window into private exotic propulsion research. The Breakthrough Starshot program, funded at $100 million by Milner, with additional contributions from Mark Zuckerberg and Stephen Hawking before his death, has the explicit goal of developing a spacecraft capable of reaching the Alpha Centauri system in roughly 20 years. The proposed mechanism, laser-propelled light sails accelerated to 20% of the speed of light by an enormous ground-based laser array, does not involve warp drive physics, but the program represents serious private investment in the fundamental physics and engineering challenges of interstellar travel. A program willing to fund laser propulsion research at the $100 million scale would not be inherently resistant to funding warp drive research if the physics developed to a point where such investment seemed justified. Several smaller private research organizations have emerged with explicit mandates to investigate exotic propulsion. The Limitless Space Institute, founded by Harold White after leaving NASA, is the most directly connected to warp drive research. The institute conducts experimental and theoretical research into space-time manipulation and advanced propulsion, with funding from private donors and research contracts. It represents the institutionalization of White's research outside the constraints of the government research environment, with somewhat more freedom to pursue high-risk, high-reward investigations. The broader ecosystem of venture-funded deep technology companies has also produced organizations working on adjacent physics. Companies pursuing compact fusion power, advanced plasma physics, and quantum sensing technologies are developing capabilities and knowledge that would be directly applicable to warp drive development at several points along the engineering path. Fusion power development, if successful, would provide the energy densities needed to begin serious experimentation with warp field generation. quantum sensing technology enables the increasingly precise measurements of nanoscale space-time effects that experimental warp drive research requires. The technology ecosystem is not converging on warp drives as a near-term goal, but it is developing the components that warp drive development would need. The competitive dynamic between national programs and private research introduces an acceleration factor that was absent in the early decades of warp drive research. When the topic was confined to occasional theoretical physics papers and small government research programs, progress was limited by both funding and institutional inertia. The entry of well-funded private organizations with genuine interstellar ambitions into the research landscape has changed the incentive structure. The first organization to demonstrate a meaningful step toward practical warp drive capability, a scalable method for generating negative energy density, a stable macroscopic warp field, a method for controlling warp bubble geometry, would gain a technological and competitive advantage of incalculable value. That incentive is real, and it is increasingly being recognized by organizations with the resources to act on it. The three competing approaches, and which one is closest to working. The theoretical diversity of warp drive research has produced three distinct approaches to the core engineering challenge, each grounded in different physics and each facing different practical obstacles. Understanding where each approach currently stands, what has been demonstrated, what remains speculative, and what the critical unsolved problems are, provides the clearest picture of where the field is heading and which direction is most likely to produce the first breakthrough. The first approach, which can be called the Casimir amplification path, is the most directly connected to experimental physics, and therefore the most immediately testable. It is the approach that produced White's laboratory warp bubble detection and represents the mainstream of current experimental warp drive research. The basic idea is to use the Casimir effect, the quantum vacuum energy suppression between closely spaced conducting surfaces, as the mechanism for generating the negative energy density that the warp metric requires, and to find methods for amplifying this effect from its naturally occurring nanoscale magnitude to the macroscopic scales needed for a useful warp field. The Casimir effect as it naturally occurs is extraordinarily small. The force between plates, separated by 1 micrometer, is on the order of millinewtons per square meter, and the negative energy density in the gap is correspondingly tiny. Scaling this up requires either extremely large arrays of Casimir cavities operating in parallel, or physical mechanisms that amplify the effect beyond what simple parallel plates produce. Several amplification mechanisms have been proposed and are being investigated. Resonance effects, in which the geometry of the Casimir cavity is designed so that quantum vacuum fluctuations build up coherently, similar to the way acoustic resonance amplifies sound in a musical instrument, could in principle produce significantly higher effective Casimir energy densities than a simple plate geometry. Metamaterials, artificially structured materials whose electromagnetic properties are engineered through their geometric architecture rather than their chemical composition, have been shown to produce anomalous Casimir forces significantly different from those between conventional conductors, suggesting that careful metamaterial design might achieve much higher effective negative energy densities. The experimental challenges are formidable but concrete. Building and characterizing Casimir cavities at the precision needed to test amplification mechanisms requires nanofabrication capabilities at the current frontier of semiconductor manufacturing technology. Measuring the resulting space-time distortions requires interferometric instrumentation sensitive to displacements at the scale of fractions of the Planck length, the same sensitivity frontier that gravitational wave detectors push against from above. The problems are hard, but they are specific enough to be attacked with existing experimental techniques and reasonable extrapolations of current technology. This is the approach closest to experimental science in the conventional sense. The second approach, which can be called the plasma field path, draws on the observation that strongly magnetized plasma, ionized gas in an intense magnetic field, can produce electromagnetic field configurations whose energy density distribution approximates some aspects of the required warp metric. This approach is more speculative than the Casimir path because it relies on classical electromagnetic effects that produce only approximate and partial versions of the required space-time geometry, rather than the quantum vacuum effects that directly produce negative energy density. However, it has the practical advantage of operating with energy scales and plasma densities that are within the range of existing technology. The same plasma physics machinery used in fusion research is relevant here. Some researchers investigating the plasma field path propose that a sufficiently intense and precisely structured electromagnetic field surrounding a spacecraft could produce space-time curvature effects that, while too small to achieve true faster-than-light travel with current energy budgets, could meaningfully reduce the effective inertial mass of the spacecraft, making acceleration easier and potentially enabling travel at a significant fraction of the speed of light with less energy than conventional propulsion requires. This is a more modest goal than full warp drive, but it represents a potentially achievable near-term application of the underlying physics that would demonstrate the concept and build the technology base for more ambitious future development. The third approach, which can be called the dark energy coupling path, is the most speculative but potentially the most powerful. It is based on the theoretical possibility discussed in an earlier chapter that dark energy is a dynamic quantum field that can be locally perturbed by appropriate physical conditions. If a physical mechanism can be found that creates localized perturbations in the dark energy field, concentrating it, suppressing it, or modifying its equation of state in a controlled region, the resulting local modification to the cosmological constant would produce space-time curvature effects directly relevant to warp drive geometry. The dark energy coupling path has no current experimental component because we have no method for measuring or manipulating dark energy at laboratory scales. It is entirely theoretical at present, but it is theoretically grounded in the same quantum field theory framework that describes all known fundamental forces, and the development of a quantum theory of dark energy, which would be required to assess whether and how it can be manipulated, is an active area of research in theoretical cosmology. If dark energy proves to be a manipulable quantum field, the energy budget for warp drive becomes essentially unlimited, and the path from theory to engineering, while still long, becomes qualitatively different. The Casimir amplification path is working its way up from nanoscale demonstrations with limited energy resources. The dark energy path, if it opens, starts with the dominant energy component of the universe. Of these three approaches, the Casimir amplification path is unambiguously the closest to experimental physics, and therefore to empirical testing. It produced the first laboratory warp bubble observation. It is the focus of most current experimental warp drive research. Its critical problems, scaling the Casimir effect to useful magnitudes, controlling the resulting space-time distortion with sufficient precision, are engineering challenges with defined research programs. Whether those challenges can be solved is uncertain, but the path is mapped. The plasma field path is being developed in parallel and may produce near-term applications in improved propulsion even short of full warp drive. The dark energy path is a long shot with enormous upside that depends on theoretical developments outside the direct control of warp drive researchers. All three are worth pursuing, and the field is pursuing all three simultaneously. The quantum physics of space-time is the missing piece of the puzzle. Every approach to warp drive development runs into the same fundamental boundary at some point, the boundary between classical and quantum descriptions of space-time. General relativity, the theory that describes how space-time curves and how warp bubbles would work, is a classical theory. It describes space-time as a smooth, continuous, deterministic field. Quantum mechanics, the theory that governs all matter and energy at small scales, is fundamentally probabilistic and discrete. The two theories are incompatible at a deep mathematical level. Their fundamental frameworks cannot be straightforwardly combined, and the unification of quantum mechanics with general relativity into a single consistent quantum theory of gravity is the most important unsolved problem in theoretical physics. For most practical purposes, this incompatibility does not matter. General relativity works extraordinarily well at the scales of stars, galaxies, and the cosmos, where quantum effects are negligible. Quantum mechanics works extraordinarily well at the scales of atoms, molecules, and subatomic particles, where gravity is negligible. The two theories can be applied separately in their respective domains without contradiction arising. But warp drive physics operates in a regime where both theories are simultaneously relevant. The negative energy density required for the warp metric is inherently a quantum phenomenon. It arises from quantum vacuum fluctuations, which are described by quantum field theory. The space-time distortion it produces is described by general relativity. A complete, consistent description of how quantum vacuum effects curve space-time requires exactly the quantum gravity theory we do not yet have. This creates a genuine theoretical gap in warp drive physics. The estimates of how much negative energy is required to produce a given space-time distortion rely on combining quantum field theory descriptions of the negative energy with general relativistic descriptions of the resulting curvature using semi-classical approximations. Methods that treat quantum effects as corrections to a classical background spacetime rather than fully quantizing the spacetime itself. These approximations are widely used in theoretical physics and are generally reliable when quantum gravity effects are small, but their accuracy in the extreme conditions inside a warp bubble wall, where spacetime curvature is intense and quantum effects are large simultaneously, is uncertain. A full quantum gravity theory would allow calculations that are currently impossible. It would provide reliable predictions of the negative energy density achievable through Casimir-type mechanisms at scales approaching the Planck length, where quantum gravity effects become important. It would describe how space-time fluctuates and foams at the smallest scales, potentially revealing new mechanisms for generating controlled space-time distortions that semi-classical analysis misses. It would determine whether the energy conditions that classical general relativity imposes on allowable stress-energy tensors hold in their full form in quantum gravity, or whether quantum corrections modify them in ways that make negative energy density more easily achievable. Progress toward quantum gravity has been slow and hard-won. Loop quantum gravity has produced a mathematically consistent framework for quantizing spacetime, but connecting it to observable predictions has been technically challenging. String theory provides a framework that consistently includes gravity alongside the other fundamental forces, but its landscape of possible vacuum states, the theoretical space of possible versions of string theory, has made extracting unique predictions difficult. Other approaches, including causal dynamical triangulations, asymptotic safety, and emergent gravity models, each offer partial insights, but none has achieved the status of a confirmed theory. What has emerged from the intersection of quantum gravity research and warp drive physics, however, is a more nuanced understanding of the energy conditions. Classical general relativity imposes the weak, strong, and null energy conditions as constraints on physically reasonable stress-energy tensors. These conditions, if strictly required, would severely limit the negative energy densities achievable for warp purposes. But it has been known since the 1970s that quantum fields violate the classical energy conditions. The Casimir effect demonstrates this directly, as does the Hawking radiation from black holes. Quantum field theory replaces the classical energy conditions with the quantum energy inequalities derived by Ford, Roman, and others, which are less restrictive and which, as noted earlier, appear to be consistent with the optimized warp drive geometries. The development of quantum gravity may reveal energy conditions that are either more or less restrictive than the quantum inequalities currently known. A quantum gravity theory might show that the negative energy achievable through Casimir mechanisms can be amplified by quantum gravity effects near the Planck scale in ways that semi-classical analysis does not predict. effectively providing a bonus energy source from the quantized structure of spacetime itself. Alternatively, it might show that quantum gravity effects impose new constraints that make certain warp geometries unstable at scales smaller than currently analyzed. Either possibility would reshape the engineering landscape for warp drive development. The investment in quantum gravity research, therefore, has direct relevance to warp drive physics, even when the connections are not explicitly drawn. Every advance in understanding how quantum mechanics and general relativity fit together is an advance in understanding the physics that warp drives operate in. The two research programs, quantum gravity and exotic propulsion, are not separate. They are different aspects of the same deep problem: understanding how space-time behaves when both quantum and relativistic effects are simultaneously important. The solution to one illuminates the other, and progress in quantum gravity research over the coming decades may deliver, as a byproduct, the physical insights that make practical warp drive development possible. Every star in the galaxy becomes a reachable DES. The scale of what becomes possible if warp drive technology is realized is worth examining in concrete terms, because the abstract concept of faster-than-light travel does not by itself convey the full scope of the transformation it would represent. The difference between a civilization confined to its home star system and a civilization with access to interstellar travel is not a difference of degree. It is a difference in kind, a transition as fundamental as the transition between a species confined to one continent and one that has crossed oceans. The Milky Way galaxy contains between 200 and 400 billion stars. Of these, current estimates suggest that roughly 20%, between 40 and 80 billion, are orbited by planets in the habitable zone where liquid water can exist on a planetary surface. The actual number of potentially habitable planets in our galaxy is therefore in the tens of billions. At a warp speed of 10 times the speed of light, every star within a sphere 100 light-years in radius could be reached in 10 years or less. That sphere contains roughly 10,000 stars. At 100 times the speed of light, the accessible sphere grows to 1,000 light-years in radius and contains roughly 10 million stars. At 1,000 times the speed of light, a speed that the physics of warp drive does not explicitly rule out, the entire Milky Way becomes traversable within a human lifetime. The nearest confirmed potentially habitable exoplanet, Proxima Centauri b, orbits the nearest star at 4.24 light-years distance. At 10 times the speed of light, it is 5 months away. The TRAPPIST-1 system, which contains 7 Earth-sized planets at 39 light-years distance with 3 in the habitable zone, is less than 4 years away at the same speed. Kepler 452b, at 1,400 light-years, is a century and a half away at 10 times light speed. A long voyage, but achievable within a generation ship or by cruise with long lifespans, and a brief hop by interstellar standards. At higher warp speeds, the same destination is a decade's journey. The implications for planetary science are transformative. We currently know of over 5,000 confirmed exoplanets, with thousands more candidates awaiting confirmation. Every one of these worlds has been characterized entirely through remote observation, through the dimming of starlight as they transit their host stars, through the gravitational wobble they impart to their stars' radial velocities, through spectroscopic analysis of their atmospheric absorption features. What we know about them is what can be extracted from photons that have traveled years or decades to reach our telescopes. In situ investigation, landing instruments on the surface, sampling the atmosphere, drilling into the crust, observing the weather, remains completely impossible for any world beyond our solar system. Warp drive access to even a handful of nearby exoplanets would transform planetary science from a discipline based entirely on remote sensing into one with access to direct physical investigation. The questions that currently cannot be answered, whether Proxima Centauri b has a magnetic field protecting it from its star's radiation, whether the TRAPPIST-1 habitable zone planets have oceans, whether any world within 50 light-years harbors complex biochemistry, could be answered by direct observation. Every nearby star system accessible to a warp-drive spacecraft would become an active research site rather than a distant astronomical object. The survival implications are equally profound. Earth faces multiple categories of existential risk over civilizational and geological timescales. Asteroid and comet impacts, supervolcanic eruptions, long-term solar evolution, nearby supernova radiation, and risks of human origin including nuclear exchange and runaway climate change. Currently, humanity has no refuge. Every human being lives on a single planet, and catastrophic damage to that planet's biosphere would be catastrophic for the species as a whole. A civilization with warp drive capability can establish self-sustaining colonies on worlds beyond its home system, distributing the human presence across multiple independent locations. The extinction of any one colony, or even the catastrophic damage of the home world, does not end the species. This transition from a single world to a multi-world civilization is the most important insurance policy conceivable for the long-term survival of complex life originating on Earth. The economic dimensions, while secondary to the survival argument, are staggering. The solar system contains enormous material resources. The asteroid belt alone holds more metal than humanity has ever extracted from the Earth's crust in all of human history. But the resources of the solar system are finite, and the resources accessible within a sphere of 100 light-years around the Sun include materials in quantities and diversities that are beyond meaningful quantification. Rare elements, exotic compounds, energy resources from the light and gravitational fields of thousands of stars all become accessible. The scarcity-based economics that have governed all of human history become inapplicable in a civilization with warp drive access to 10,000 star systems. The question of extraterrestrial life, currently limited to remote detection through spectroscopic signatures and the listening programs of SETI, becomes a question that can be answered by direct investigation. Warp drive exploration of nearby star systems would provide definitive answers about whether life has independently originated elsewhere. Finding microbial life on a second world would establish that the origin of life is a general phenomenon rather than a unique accident, while finding complex or intelligent life would transform human civilization's understanding of its place in the cosmos in ways that are difficult to even fully imagine in advance. Every star visible in the night sky is a destination. Every one of those points of light hosts worlds that are currently as inaccessible as the Moon was before 1969, but less remote in light travel time than the Moon was when Julius Caesar lived. Warp drive does not change the distances in any absolute sense. The stars are where they are, and the light years between them remain as vast as they have always been. What it changes is whether those distances are barriers or merely measures. The cosmos becomes not a prison from which there is no exit, but a landscape of extraordinary richness and variety waiting to be explored. The question that warp drive research is working to answer is not whether we want to go. Every human being who has ever looked up at the night sky and wondered has answered that question already. The question is whether the physics will let us. Warp drive development, physics, scaling limits, and timelines. Any honest assessment of the distance between current experimental capabilities and a working warp drive must begin by acknowledging that the distance is large. This is not a technology whose commercial deployment is around the corner, or a physics problem whose remaining puzzles are minor details awaiting cleanup. The challenges that remain between where warp drive research stands today and where it needs to reach to produce a working prototype are substantial, and some of them may involve physics that has not yet been discovered. An accurate picture of the timeline requires being clear about what specific problems need to be solved and what would constitute a genuine breakthrough at each stage. The most immediate challenge is the scaling problem for negative energy generation. White's team produced a nanoscale warp bubble geometry through Casimir cavity manipulation. The bubble was real in the sense that its spacetime geometry matched the theoretical warp metric, but the total spacetime distortion it produced was immeasurably small as a propulsive effect. Scaling this from nanometers to the meter scale region, needed to surround even a small spacecraft, requires increasing the linear dimension by a factor of roughly 10 billion, which translates to an increase in the required negative energy by a factor of at least 10 to the 30th if the energy scales with volume. Even the most optimistic geometric efficiency arguments do not bridge a gap of this magnitude through geometry alone. Something qualitatively new, a physical mechanism that amplifies the Casimir effect by many orders of magnitude, is needed. Proposed amplification mechanisms include resonant Casimir cavities, metamaterial enhancement, and quantum entanglement-assisted coherence across large arrays of Casimir structures. None of these has been demonstrated to work at the required amplification levels. They are theoretically motivated proposals whose feasibility depends on detailed physics calculations and experimental tests that are in early stages. The Casimir amplification problem is, by most assessments, the single most important unsolved problem in practical warp drive development. Solving it would transform the rest of the engineering challenges from purely theoretical exercises into concrete engineering problems with defined specifications. Assuming negative energy generation at useful scales is achieved, the next challenge is field control, the ability to shape the generated negative energy density into the specific spatial configuration required by the warp metric. The warp bubble requires not just a certain total amount of negative energy, but a precise spatial distribution, concentrated at the bubble wall in the pattern described by the metric, with a specific relationship between the forward contracting and rear expanding regions. Achieving this level of field control requires both the ability to generate negative energy at specific locations with high spatial precision and the ability to measure the resulting spacetime distortion with sufficient accuracy to verify that the intended geometry has been achieved. The measurement challenge is itself non-trivial. Detecting and characterizing macroscopic spacetime distortions at the level required for warp field verification would require gravitational sensing technology significantly more sensitive than anything currently available. The development of quantum gravity sensors, devices that use quantum mechanical effects to measure gravitational fields with extreme precision, is an active research area with applications in geodesy, navigation, and fundamental physics that justify investment independent of warp drive research. Progress in quantum gravity sensing technology contributes directly to the measurement infrastructure that warp drive development needs. Power generation at the required scales represents a third independent challenge. Even the most optimistically reduced exotic energy estimates for an optimized warp bubble still involve total energies equivalent to significant fractions of a gram of mass, converted completely to energy through Einstein's equation. For reference, the atomic bombs dropped on Japan in 1945 released energy equivalent to roughly 1 gram of matter each, and they represented the most energetically dense devices that existed at the time. A civilization capable of producing and precisely directing warp drive scale energies into specific quantum vacuum manipulation configurations is a civilization that has also solved controlled nuclear fusion power and possibly advanced further. The energy requirement for warp drives is not the bottleneck that prevents near-term development. The negative energy generation and field control problems are more fundamental, but it establishes the energy infrastructure baseline that a warp-capable civilization must exceed. Given these challenges, what are realistic timelines? The honest answer involves large uncertainty, because breakthrough timelines in physics are notoriously difficult to predict. Transformative discoveries arrive on their own schedule, not on the schedule that extrapolation from current progress would suggest. The transistor was not a predictable extrapolation from vacuum tube technology. It required quantum mechanical understanding of semiconductor band structure that was not available until quantum mechanics was developed. Laser technology similarly required quantum mechanics and could not have been predicted from classical optics. Warp drive development may be in a similar position, waiting for a conceptual breakthrough in quantum gravity or quantum vacuum physics that suddenly makes the scaling problem tractable. If that breakthrough arrives in the next decade, it is not implausible that laboratory-scale demonstrations of macroscopic warp field generation could follow within 10 to 20 years, with engineering development toward a prototype vehicle taking another several decades. A first warp vehicle operating at a fraction of the speed of light, not yet interstellar but demonstrating the principle at scale, within 50 to 100 years from a breakthrough is not an unreasonable extrapolation once the key physics problem is solved. If the breakthrough takes longer to arrive, or if it reveals fundamental obstacles that are more severe than current analysis suggests, the timeline extends accordingly. Some physicists believe the scaling problem has no solution within known physics, and that an entirely new physical mechanism, something that does not yet exist in the theoretical literature, will be required. This possibility cannot be ruled out, and if true, it pushes the practical timeline beyond any meaningful estimate. Physics has surprised us before with the depth of what was unknown, and it may do so again. The wall was never the end of the road. For over a century, the speed of light was presented as physics' final answer to the question of how far humanity could reach. Einstein's equations were correct, the particle accelerator experiments were unambiguous, and the conclusion seemed inescapable. The wall was real, the wall was permanent, and the stars would remain forever beyond reach. This was not a pessimistic interpretation of the physics. It was the straightforward reading of the best confirmed theory in science by the best physicists alive. The wall was not a mystery to be solved. It was a settled fact to be accepted. What the story of warp drive research reveals is that settled facts have fine print. Einstein's equations did not say that faster than light travel was impossible. They said that objects moving through space could not exceed the speed of light. The distinction between objects moving through space and space itself moving was not a loophole someone invented to circumvent the physics. It was a feature of general relativity that had been sitting in the equations since 1915, acknowledged by theorists as an interesting mathematical curiosity, and then taken seriously by a graduate student in 1994 who decided to calculate what it would actually require. The wall turned out to have a door. Finding the door required someone to look for it rather than assume it was not there. The Casimir effect existed and was measurable long before anyone connected it to warp drive physics. Negative energy density was a confirmed experimental phenomenon before White's team detected warp bubble geometry in a Casimir cavity. The physics that makes warp drives theoretically possible was not waiting to be invented. It was waiting to be recognized and assembled. The assembly is still incomplete. The energy scaling problem is unsolved. The field control challenges are formidable. Quantum gravity remains unfinished. But the assembly has begun, and the direction it points is clear. The scientific enterprise that produced relativity, quantum mechanics, and the standard model of particle physics is the same enterprise now working on quantum gravity, quantum vacuum manipulation, and exotic spacetime geometries. It has a record of solving problems that seemed insolvable, of finding that apparent limits were really approximations to a deeper physics that changed the picture entirely. There is no guarantee that warp drive will follow this pattern. The universe is not obligated to provide the physics we need for the destinations we want to reach. But the history of physics is a history of walls that turned out to have doors, and the people working in laboratories and at whiteboards on the problems described in this story are looking for the next one. The stars have not moved. The distances between them have not changed. What is changing is our understanding of whether those distances are permanent barriers or temporary descriptions of a cosmos that physics has not yet fully explained. Every experiment that measures the Casimir effect more precisely, every theoretical paper that refines the energy requirements for an optimized warp geometry, every gravitational wave detection that teaches us something new about how space-time behaves. Each of these is a step toward an answer. The answer may take 50 years or 500, but the question is being asked with real mathematics, real experiments, and real institutional investment for the first time in history. That is not nothing. That is how revolutions in physics begin.